Let's start now on the divergence theorem. So what are we trying to do here? You can see that we related a line integral to a surface integral. And you'll see that the line integral that we considered was for a closed path. I'm going to start off with something similar. I'm going to do an area integral now, and the area will be a closed area. So I'm going to imagine integrating over the surface of a small box. Okay? And I want to look at what that area is. So let's write down what we want to do. So I want to integrate. It's going to be a closed area. Okay, so again we come to notation. So let's see. V dot dA. Okay. Guys, I like to write an area integral like this. Okay, I just remembered now. Maybe some of you would prefer this. Did you used to use that? Okay, so some said no, some said yes. I'm not going to use that. Okay, I like to use that for an area integral. So I don't look at how many signs there are going through the circle to tell me what integral it is. I look at the measure. Okay, is this a little area? Is it a little line? Is it a little volume? So that's where I'll look to learn what kind of an integral this is. So when I write it like this with one integral sign, that doesn't mean that it's over a line. This is an area integral. Okay? And I want to integrate over the surface of a small box. Okay? So there is my small box. Good. Where should I evaluate V? So let's say I'm integrating over the front of the box. What value for V should I take? It's a very small box. So what value of V should I take? Center of the side. So what I'm going to do is, at the middle of each side, I'm going to see what is V at that point, and I'm going to use that value for V all over the side. If I chose some other point, let's say I chose the top corner of each side, okay? My answer would not change in the limit that these boxes become very small. Okay? So I could pick any point to evaluate my field. I'm going to pick the center of each side. Let's set up some axes. So let's say this is Z, Y, maybe that's going at the back there. Maybe that's the X direction. And let's say that this corner of the box is at the origin. Okay. So here's my box sitting there. This corner is at the origin. The length of the three sides are exactly the same. Okay. Now. Yep.
The sequence should be X, Y, and Z.
So do you want a right-handed coordinate system? It doesn't matter. Is that what you'd like, Malcolm?
Yeah, I'm just thinking that's what we normally use.
So let's see. So let's put our hands like this. Okay, so what's the right-handed, left-handed coordinate system? This goes X, Y, Z. Okay? For left-hand coordinate system, X, Y, Z. So if you would like a right-handed coordinate system, okay, then if we want to call this direction X, that direction will be Y, and that direction will be Z. Prefer that one?
I'm just thinking if we're going to do something that's crossing dx and dy, then you'd like to get to these
Oh, you know, you can derive all of these integral theorems with whatever conventions you want. And if you use the conventions correctly for your coordinate axes, I'm happy with whatever, just as long as you're consistent. Okay? Good. Okay, so let's use the coordinates like that. Now, can someone tell me, okay, we'll make this a small box. So what will the length of this side be? Dx. What will the height of this side be? And what will that depth be? dy. Good. In fact, you know what? I'm going to shift my origin to make it slightly more general. Let's make this corner of the box to be a point x, y, z. If I look at the top surface of the box, can someone tell me what dA will be for the top of the box? So dx, dy, that will be the area of that side, but now we need to decide on a direction. And there's two natural directions we can pick. Either dA points inside the box or outside the box. Okay? For this problem here, whenever we write this, we're going to assume that dA points outside. Okay? If we assume it points outside for the top of the box, what is the direction? Z. Good. So for the top of the box, dA will be equal to dx dy z hat. What will it be for the bottom of the box? It will be? Good. So for the bottom of the box, the area is the same. It's still dx dy. Except that now if we're pointing out the box, it points down. Good. Let's call this, so there will be a left and a right, and there will be a front and a back. So I want you guys to write down the answer for the front and the back, and for the left and the right. Will you guys write down the dAs for those sides now? Can someone tell me dA for the front of the box? D, dz, dx, minus y hat. Good. For the back? What is it? D, z, d, x, y hat. Very good. For the left side, Good. For the right. Good. Are we happy with that, guys? So now,
excuse me.
yes.
Let me carry back to our direction, the orientation. We said we're taking outside the path. Now, I remember we're discussing the divergence when we are coming towards the point and when we are going away from the point. Now, a matter in terms of maybe physical interpretation. Now, what would this matter if we are taking the direction inside? What would have been the difference?
Okay.
As compared to this?
Good. So what will happen is, if we took the direction to be outside or inside, all of our dAs would be related by a minus sign. So dA pointed outside, calculate that answer, compared to the answer of dA pointing inside, all you would pick up would be a minus sign. And you would get another integral theorem. So what we're going to relate here is the integral of v dot dA to something. If you chose a different direction for your dAs, your theorem would have an extra minus sign in it. That's the only thing that would change. But you would still get a relationship between two different quantities. Okay? Actually, you know, whenever you have a choice for these signs, okay, so everybody has got their favorite convention. Okay? Whether, I mean, some people like to use right-hand corner systems, sometimes you'll see people using left-handed. There's all of these different conventions that you can choose. What I would really encourage you to do is make sure that you can write down all of these different laws and theorems, no matter what the conventions are that someone chooses. So here you're right, we chose dA pointing out. Is there another choice that we could have made? Yes, dA pointing in. Both of those will give you a valid mathematical theorem. You can derive it for either case. I would encourage you to be flexible enough that you can calculate for all of those different cases. If you can, then you've really understood what you're talking about. The further you go in physics, there's more and more conventions. Another very popular one is some people use what's called the plus, minus, minus, minus metric. We'll talk about that later in the course. Other people use a minus, plus, plus, plus. And really, I'm telling you, when you read a paper, the first thing that you're going to have to decide is what conventions are they using, and half the time it won't be the conventions that you usually like. And you're just going to have to get good at being able to translate the equations from your conventions into the conventions that somebody else uses. And that tests your understanding. Can you translate between these different conventions? Okay? You happy? Good. Any other questions? Okay. So now, what I want us to do is to actually evaluate that integral. So the integral of v dot dA will be equal to a sum over the 6 sides of the box, and we want v at the midpoint dotted into dA. So let's write down what this is. Oh, so this is again a choice that you can make. So I was saying midpoint. Would you like to work with the corners? Okay. So you're right, the corners is easier, okay, in this particular calculation, but it really won't make a difference, okay? Let's stick to midpoint, okay? You can do it with corners. Okay, midpoint dot dA. Can someone tell me what's the midpoint of the bottom of the box? X plus dx over 2. What's the y coordinate? Y plus dy over 2. What's the z coordinate? Z. So the first term for the bottom of the box will be v x plus dx over 2 y plus dy over 2 and dz. And this will be dotted into dA for the bottom of the box, which was minus dx dy z hat plus. So this is for the bottom of the box. Can someone tell me what we'll have for the top of the box? X plus dx on 2.
Y plus dy on 2.
Y plus dy on 2.
Z plus Z plus dz on 2.
Z plus dz on 2. Alzar? Oh, very good. Okay, this should be Z. That was another little test. Good. Z plus dz on 2, is it? Z plus dz, because we've gone all the way to the top of the box, right? So just Z plus dz. Dot into? What is it for the top of the box? Dx, dy, z hat. So this is for the top of box. Good. Did you guys understand it? You've got another 4 sides to test. Write down the answer for the next 4 sides. For the left side, what did you get? V into
minus dy
plus. What's the next side?
right?
Yes?
X plus dx.
Yes?
Y plus dy. Z plus z.
Good. Dot into?
Dy dx. Dy dz.
Good. Very good. Okay. Is somebody else going to give me the front and the back?
X plus dx on 2. Y Z plus dz on 2.
Good.
Times minus dz dx y hat.
Very good.
That's the front.
Good.
So for the back, we have b into x plus dx on 2. Y plus dy and z plus dz on 2
Good. Into?
into dz and dx y hat.
Perfect. Thank you. Are we happy with that, guys? Good. What's the next step? Now we Taylor expand these terms. So this is equal to, now look at the first term. So I'm going to take v x, y, z plus, now there's a dx over 2. So we will have, oh, sorry, I'm not going to take v. I've got v dotted into z hat. So what will I pick up? vz. Good. And I'm going to keep track of the minus here. So there's a minus vz at x, y, z. Then I've got a minus dx over 2 because I'm shifting x plus dx over 2. I will have a dx dy and a dvx dx and a minus dy over 2 dy dx dy dx dy. So this is what I get from the bottom of the box. So let's make sure that we're happy. This term here, I'll get a dx, because of that change there, I'll get a dx over 2 times the x derivative. It will be the x derivative of the z component of the field. Oh, so there was another little test for you guys. So this will be a derivative of the x component of the field, dx over 2 because that's the change, and there's the dx dy and the minus sign. And then this term over here with the dy over 2 is because we've shifted the y coordinate. Okay? And then we have got plus, and now from this term we get again the z component of the field. There's a dx dy, so we will get the z component x, y, z. We have got plus dx over 2, dx dy, dvz, dx. Because the y coordinate is shifted, we've got plus dy over 2, dx dy, dvz, dy. And now the z coordinate is also shifted. Yep?
I think there is an extra dy and plus bracket. dy over 2 dy dx dy.
Where? Oh, good. Okay, you guys are not getting all of these little tests I'm giving you. Good. Okay. One guy passed. Okay. There. And then there's one more term because z also shifts. And, yep.
So why aren't you multiplying dy dx with the term of the Taylor expansion as well?
Good. This should be multiplied by dx dy. Okay. I think that looks perfect now. Now, let's start collecting terms. There's dx dy vz, dx dy vz, but with a minus. So that will cancel against that. Minus dx over 2 dx dy dvz dx, dx over 2 dx dy dvz dx. So that will cancel with that. Minus dy over 2 dy dx dvz dy, dy over 2 dx dy dvz dy. So that will cancel with that. And that's the only term that's left from the bottom and top of the box. What I would like you guys to do now is do exactly the same, and I want you to tell me what term is left after you have treated the left and the right and front and back. Okay? So try to combine those now.